All right, so welcome to our lecture meeting for Tuesday, September 3rd. Happy long Labor Day weekend, so hopefully you enjoyed the extra day off. Um, we'll start today with the quote of the day. This is actually a comic of the day, I suppose. It's from XKCD Comics. The comic number is 2899, and uh, there are two folks standing here talking to one another, and one guy says, when a metric becomes a target, it ceases to be a good metric. And the other one says, sounds bad. Let's offer a bonus to anyone who identifies a metric that has become a target. So thereby creating a target from that metric. This idea, I think, applies pretty broadly. A lot of the times we're looking at a particular, whether it's an aspect of our life or whether we're in the corporate world looking at an aspect of our business, and we say, we're not really happy with how this is, proceeding. This might be somebody looking to lose weight, or this might be a corporation looking to say increase customer satisfaction or something like that. And then we say instead of asking the deeper and more difficult question of like, okay, what is it that we actually want and how do we actually achieve that? We just say, okay, well, the thing that brought this to my attention was this number. Let's make the number look better instead of making the underlying thing better, right? So, maybe with weight loss, that means that somebody ends up dehydrated because if you dehydrate yourself, you lose a lot of weight really quickly, and that makes that number look good, but that's not healthy overall, right? Or the same thing applies to businesses. A lot of times incentives are set up that where it's like the best way for an employee, and best in some sense, not maybe most ethical, but the best way for an employee to meet that number is for them to do something very unethical, or for them to basically destroy the business to make that one number look better. The classic example of this, that there's several of these kind of examples. I don't know how true any of them are, but they make the point pretty clear. Is like certain geographic areas infested with certain, whatever type of animal they don't want there. I think some of them, there's some that go with snakes in a certain area and some that are like rats in a certain area. Um, and so the government says, hey, for anybody who brings in, one of these dead animals or their pelt or their this or that, identifiable body part, proving that you killed the animal, then we'll give you compensation. We'll give you $1 for every rat you bring in, let's say, right? And so you say, okay, we have too many rats. We want to get rid of the rats, bring in dead rats. That should fix the problem. But then people start breeding rats so that they can kill them and bring them in to get the dollar, right? Um, so I mean, like I said, I don't know. There's kind of several variants of that story. I don't know how true any of them are. But it at least makes the point that, you have to be very careful when you set up an incentive structure and when you have a number uh, that is a metric that is kind of related to the thing you're trying to fix. Be careful that you don't try to game the system and just make that number look good and neglect the thing that you're trying to fix, uh, as a result of just looking at that number. So I think that's, where does that apply to the corporate world? Well, if we put compensation, just equivalent to share price, for instance, for some executives, maybe that's not, you know, the way to encourage, say, ethical business practices or business practices that create long-term good business relationships. So, so anyway, I think lots and lots of applications of that idea. Okay, so the plan for today is to finish section 2.6 on solving compound inequalities, start 3.1 graphing linear equations of two variables, so starting chapter 3. One important note is the graphing tool on WebAssign, that you use to kind of enter your graphs. It's a little bit there's a little bit of a learning curve to it. Once you've used it a few times, it's really straightforward to use, but just figuring out what you need to click and where can be a little bit of a learning curve. So there's a supplement posted on Blackboard. Sorry, my allergies are like haywire today. I was mowing grass over the weekend, and uh, so, but there's a graphing tool supplement posted on Blackboard. Let me just bring that up over here. And now my computer does not want to select my Google Chrome window. I thought I had the tech issues sorted out, but well, Chrome just froze on me, so not good news as far as the tech is concerned. But anyway, so on Blackboard, if you go to our Blackboard site, you can look under the recently made available folder supplemental material, and you'll see that there are two graphing supplements on there. One of them is for graphing equations, just kind of basic use of the graphing tool. And you can take a look at that. That has some information on it. We'll also hopefully review the WebAssign graphing tool. I might have to restart Chrome for that, but we'll pop up WebAssign and we'll go through a problem or two on there just to see how it works. The plan for Thursday is to cover sections 3.2 and 3.3, talking about the slope of a line and finding the equation of a line, and also do a bit of review of how to use a graphing calculator. So, how to graph lines on the calculator, use the graphing functions, the y equals screen and all of those. We're not going to spend a lot of time working with the calculator. Most of the work in the course is going to be kind of working with this material by hand, but we will touch on the calculator here and there. And the calculator is a great tool to say check and answer in this chapter. And then, as I mentioned, the supplemental videos, keep an eye out for those coming up here. Any questions on anything that we discussed up to this point? Let me try really quick just to get my Chrome sorted out here. I'm going to try to close it and reopen it. And that seems to usually work for tech things. So we'll see if that works here. Okay. Yeah, I closed it and reopened it, and that did seem to work. So let me switch my share really quick here. And again, if you're in our Blackboard site, let me change the mode here. In the Blackboard site, supplemental material brings up these references. There's also a little document in here, WebAssign shortcut keys. As we move into the more algebraic topics, these can be useful. So things like entering square roots or things like entering exponents, stuff like that. These are just some shortcut keys. So you can, type a little bit more quickly in WebAssign. You don't need to use those. You can use the little calc pad or math pad over on the right. But sometimes that makes entering answers a little bit quicker. And then this WebAssign graphing quick reference just gives a bit of a rundown of how to use the graphing tool WebAssign. Again, we'll go through a couple examples today, but this will give you, another resource that you can look back to. Okay, let me get my windows squared away here, and then we'll jump into it. Let me actually close these, since that wasn't all that happy before. We'll close these windows out. Okay. All right, so jumping into the material now. We're just gonna, we did a couple of these inequalities last time, these compound inequalities. We're just gonna do these last couple, wrap up this section, and then jump into chapter 3. So we saw last time that when we have a compound inequality like this is kind of like saying 4x minus 1 greater than or equal to -5 and 4x minus 1 less than 7. So we saw compound inequalities where we had two inequalities attached to each other with either the word and or the word or. If we have an inequality like this is really just two inequalities attached to each other by and. I keep going back and forth between using one screen or using two screens, trying to get my tech to work a little better here, and every time I switch, it changes the way that my trackpad works, so I have to get reused to writing fairly legibly. So really, this compound inequality that we see over here, -5 less than or equal to 4x minus 1 less than 7, really stands for these two inequalities, and these have the special characteristic that for each inequality on one side of them, we have the same expression. So we can kind of tie these two together. The nice thing about having inequalities put together this way is when I do an equation solving step, or I suppose I should call it an inequality solving step, but they're mostly the same steps. The process is mostly the same. Well, instead of having to solve this one and then solve this one separately, I can just do the same step to all three pieces, to all three expressions, the left one, the center one, and the right one, and I can solve these more efficiently. What does a solution look like? A solution looks like instead of just say x less than number or x bigger than or equal to number, it looks like x between two numbers. When we do an equation solving step, we maintain the strictness or non-strictness of the inequality. So let me just make a little bit more room here, and we'll work with our compound inequality over here. So I see in the middle, I have a 4x minus 1. I would like to get just an x in the middle. Right now in the middle, I have an x term as well as a constant term. Let me just get rid of that constant term to start with. Move all the constants off of the term with the variable in it. So I do that by adding 1 to the middle. So the -1 and the +1 cancel. But then I have to add 1 to each of the sides, the left side and the right side as well. My middle now is just 4x. I have a strict less than. That stays the same sign. The strictness as well as the direction is less than 7 plus 1 is 8. And on the left side, I have a 4x is greater than or equal to -5 plus 1 is -4. I've isolated the variable term in the middle. Now I want to isolate the variable itself. So I divide this middle term by 4. That's going to get the x by itself. If I do that to any one of these three pieces, I have to do it to the other two as well. So I divide by 4 in all three places. This is not a negative number. I'm not multiplying or dividing by a negative, so I don't have to switch the inequalities. If I was multiplying or dividing by a negative, I would just switch all of the inequalities to point the other direction. But I'm not, so 4x over 4 is just x. Strict less than 8 over 4 is 2. And then greater than or equal to -4 over 4 is -1. So there's the algebraic representation of my solution. I have an interval notation, close -1 to open +2. And I have a graphical representation. I draw my real line. My points of interest are -1 and 2. I want to include -1 because that's a greater than or equal to. So I'll put a closed dot there. Again, I'm kind of over exaggerating this so you can see it on your screen. And then I have a strict inequality on the right, so I want an open dot at 2. And my x should be between those two. So I have an algebraic representation, an interval notation representation, and a graphical representation of the solution. Any questions on this one? So you can see that this is more efficient than, say, solving two inequalities attached with and, But this only applies whenever we can kind of glue those two inequalities together because they share a common expression, right? For kind of an arbitrary, uh, expression less than expression and expression bigger than expression or something, we won't be able to glue them together for most cases, but sometimes we can, and when we can, it's a little more efficient to solve it. Okay, and if we look at this last example in this section, again, we see this compound inequality where we have three terms, 3 less than or equal to negative 2x plus 3 less than or equal to 10. I should have said 3 expressions instead of 3 terms. So we have 3 expressions all related to one another. When I go through my strategy to solve the inequality, again, whenever I do something, I just apply it to all 3 expressions. So I have this negative 2x plus 3. Clearly, this is my component where I want to isolate the variable term, isolate the variable, get an algebraic representation of the solution, and then represent that in interval and graphical form. So I'll start by getting the variable term by itself by subtracting off 3. Now I'm subtracting here. Since I'm subtracting, I'm just kind of moving left or right along that real line. The inequalities all stay the same. So 3 minus 3 is 0. That's still a less than or equal to. Negative 2x plus 3 minus 3 is just negative 2x. That's still a less than or equal to. 10 minus 3 is 7. All that I did was subtract a number. So I kind of, I have my scales balanced, and I just took 3 units off of each of the plates of the scale. It still all balances the same way. But now I want to isolate my variable by, say, dividing by negative 2. Now I'm going to have to change my direction of my inequalities. So now, since I'm multiplying or dividing by a negative number, I'm flipping over that real line, and kind of the negative direction becomes positive and the positive direction becomes negative. So 0 divided by negative 2 is 0, but less than or equal to dividing by negative, we got to flip it, becomes bigger than or equal to. Negative 2x over negative 2 is just x. Again, less than or equal to becomes bigger than or equal to because we're dividing by a negative, and we get negative 7/2. As a side note, if we had forgotten to flip our signs, we'd have got 0 less than or equal to x, less than or equal to negative 7/2. How can that be the case? How can 0 be less than or equal to negative 7/2, something that's negative? Clearly something went wrong there. When we were careful and we flipped our signs as needed, we do have that 0 ought to be bigger than or equal to some negative number. That does make sense. So that's a little check that we can always do. There's a lot going on in these problems, so having little checks like that we can recognize and just make sure that we didn't make any silly mistakes. Really helpful to have those kind of checks. I can write this in interval notation. These are both non-strict inequalities, are both greater than or equal to's, so I want to include both endpoints. I don't want to write this as closed like 0 up to negative 7/2. I want to respect the order, the natural ordering on the real line of these numbers. So the negative 7/2 goes to the left, the 0 to the right. Just because we had it written algebraically this way, we should always write it in interval notation the correct way. In algebraic notation, it doesn't matter so much which direction you put it. And then representing it graphically, our points of interest are 0 and negative 7/2. Of course, negative 7/2 is to the left of 0. We do want to include both endpoints. and the interval in between them. So that will be the graphical representation of our solution. Any questions on any of this so far?
Yeah, can you repeat that process with the graph thing again? I'm sorry, I missed that word.
Yeah, sure. Yeah, so with the graph, so if we look at our interval notation, we have our solution set is the interval from -7/2 up to 0, with the closed brackets means we include the endpoints. Or you can think of it as our solutions for x are between 0 and -7/2, and the non-strict inequalities, the greater than or equal to's, mean we include the endpoints. So the first thing that I do is draw out a number line. Then I ask myself, well, like, what are the points of interest? What are the points that I want to mark on here? I could go through and mark, -3, -2, -1, 0, 1, 2, 3, but I'm only going to choose to mark the points of interest. So here, -7/2. That's going to be an important point. That's our left boundary for our solution set, and 0 is going to be important because it's the right boundary for our solution. Now I know my solution set lives between these two, so in here. But before I go and draw that, I want to ask myself about the endpoints first. It's a little easier to draw the endpoints before you draw the middle section. So I'm going to look at -7/2. Should I include that or should I not include that? I can look at either the interval notation or the inequality related to the -7/2. And in both cases, I see that I do want to include that endpoint. I have a closed interval on that end in the interval notation, and I have an x greater than or equal to -7/2. So I do want to include -7/2 in the solution, because if x was equal to 7/2, then it does satisfy x greater than or equal to -7/2. And then similarly for 0, again, I see 0 comes with a closed interval in its side, or the inequality related to 0 is x less than or equal to 0. So x equals 0 is a solution. So I'll include x equals 0 as well. And then I want to, either by looking at this interval or this interval, the rest of my solution is the interval between -7/2 and 0. But I've just been careful to include both endpoints.
Thank you.
Yeah, you're welcome. Any other questions?
Yes, I have one.
Yeah, sure.
In the first problem that you did, like before this,
Mhm.
so the parenthesis, because you have a bracket and then a parenthesis,
Mhm. Yep.
is because of the sign.
Yeah, exactly.
So if there's no or equal to, it's going to be a parenthesis.
Yeah, exactly. So because this is a strict inequality, it's x less than 2, not x less than or equal to 2. That gives us the open parentheses instead of the bracket in the interval notation, and that gives us the open dot instead of the closed dot in the graphical representation. Yeah, exactly.
Okay.
Yeah, so all of those kind of relate to one another. This sign, this parentheses, and this open dot versus, say, this non-strict inequality, the greater than or equal to this closed bracket and this closed dot. Yeah.
Okay.
Yeah, good questions. Anybody else, any questions before we move on? Yeah, part of the challenge of math, part of it, of course, is learning the mathematical concepts and the ideas and all of that. But part of the challenge, maybe even a lot of the challenge, is, essentially learning the language. It's kind of like you're learning to speak another language while you're learning to think in that other language. So there's just a lot of different symbols and notation and so on. And it's a little bit like learning another language. And, the first couple of times you do it, it's like, wait, what was the parentheses versus the square brackets? And it's a little tough to wade through and you have to look back at your notes. But by the 10th or 15th time, you're a little more fluent, so to speak. And, by the 30th time you've seen this, you're like, oh yeah, okay. It's just, you look at it and it's just automatic. So it's like gaining fluency in a language while you're kind of learning new ideas and new ways to think in that language. I think that's one of the reasons that we see a lot of the same material repeated throughout even like 080, 090, 108, 111, 142. Like, you go, if you went through these 5 courses that kind of build on each other, we see some of the same material repeated throughout them. And part of it is that when you're more fluent, you can investigate the ideas more thoroughly and more easily and more broadly. So kind of at the earlier stages, it's more about building up fluency, and at the later stages in that progression, it's more about kind of like building up mastery, getting the ideas down now that you have the fluency. And 108 is kind of that like middle ground where still working a little bit on the fluency, still working a little bit on mastering the ideas. Any other questions on compound inequalities before we move on? Okay, great. So let's look at a couple examples in section 3.1, graphing linear equations of 2 variables. And I'm going to actually write myself a note down here so I don't just kind of get going and plow through. After the second example, we'll jump over to WebAssign, take a look at that graphing tool. And, after we do a couple of these, that should refresh the idea in our mind a little bit. We can take a look at the graphing tool then, see how that works, and then come back and do a few more examples. All right, so let's consider this linear equation. We've seen linear equations in chapter 2, but we saw linear equations in one variable, like, 2x plus 1 equals 5. And we said for at least this is kind of the typical case, the case that we usually expect in a linear equation. For a case like this, we see that x equals 2 is the solution. In other words, it's the one and only solution. If I substitute in 2 for x, I get 2 times 2 is 4, plus 1 is 5. That is a true statement. If I pick any other number for x, 0 or 100 or -3/2, whatever, and I do my arithmetic simplification, the left side and the right side are not going to be the same number. So I have exactly one solution. Now, if I have a linear equation in 2 variables, like this one here, 3y plus 6x equals 18, well, now I kind of have 2 things that can move. I have 2 what we might call degrees of freedom. And I have this one constraint that I'm requiring this relationship between x and y. But if I have kind of 2 dimensions of freedom and 1 dimension of restriction, I still have kind of 1 dimension of freedom left over. If I told you like I'm standing in this position north and south and this position east to west, that's kind of 2 dimensions that I need to give you to tell you where I'm standing. If I said I could be standing anywhere, but I'm standing in this position north south, but I didn't tell you where I was standing east to west, you have 1 constraint, but I could be still like almost anywhere over the globe, as far as east to west is concerned. So that's a little bit like what's happening here is we can, in some sense, choose x any way we want, choose y any way we want. But we do have 1 constraint. We need to be subject to this equation. We need to choose x and y in such a way that this equation holds true. And essentially what this means is that once I pick x to be whatever number I want, I can, in most cases, there are some edge cases like we've seen before, but in most cases, I can pick x any way that I want. But once I've picked x, that tells me what y has to be. Or I can pick y any way I want, but once I pick y, it tells me what x has to be. Sorry, my allergies are just going haywire this morning. Okay, so we have a table over here, a list of X and Y values. And one of the things about graphing lines is we know that 2 points determine a line. So if I have 2 points, there's a unique line that goes between them. Oops, if I can draw my line correctly. So if I tell you these are the 2 points of interest and they're 2 distinct points, there's exactly one line that goes through them. As a usual kind of pretty good practice, I'll typically look for 3 points on the line. I'll use 2 points to graph, and then a third point as a check. If I'm claiming that all 3 of these points are on the line, then if I end up with a third point that is not on the line between the other 2 points, then something went wrong. I want to go back and check my work. So that's what we're going to start with here. We're going to look for 3 points that are on this line. In other words, we're looking for 3 combinations of X and Y that satisfy this equation. Now in practice, or in theory, I can choose these kind of any way that I want. I could choose X to be 17 million and figure out what Y is, or I could choose Y to be, 6.15 and figure out what X is. In practice, I probably want to pick nice numbers. So for instance, the coordinate axes, the intercepts of the axes are usually pretty nice places to start looking for answers. So I might want to plug in X equals 0. Now, if I choose X equals 0, what does that mean for my equation? That means that 3y plus 6 times 0 has to be 18. But this term just goes away. This term is just 0. So I have the 3y has to be 18. Y equals 18 over 3, or 6. So if I choose X to be 0, then Y has to be 6. If I were to choose, say, X to be 2, then what does my equation say the Y has to be in that case? Well, 3y plus 6 times 2 equals 18. 3y plus 12 equals 18. So we see that we just have a linear equation in one variable now that we need to solve. Subtract 12 from both sides and get 3y equals 6. Divide by 3, y equals 6 over 3 is 2. I'm going through these pretty quickly, but I hope at this point we're pretty comfortable solving linear equations. And I don't have to just pick values for X and find the associated value for Y. I can do it the other way. I could pick a value for Y and figure out what the associated X value is. So if I pick Y equals 0, I get from my equation 3 times 0 plus 6x equals 18. Three times 0 is 0, I get 6x equals 18, or x equals 3. And so I now have 3 ordered pairs. I now have 3 xy coordinates. I could write them in this notation, like 0, 6, 2, 2, and 3, 0. And I could come down to my Cartesian plane. So I'm looking for 0, 6. In other words, x equals 0, y equals 6. That point is there. Maybe I'll actually draw it in blue instead. You can see it a little bit easier. That's 0, 6, x equals 0, y equals 6. By convention, we usually write it x, y. The third point, 3, 0, is also pretty easy to locate. That's when x is 3 and y is 0. So that's on our x-axis down here, 3, 0. This is 0, 6 up here. And then 2, 2 is x equals 2, y equals 2. That's like about here. If I connect the 2 points on my axes with a straight line, and then I asked, does that third point that's not on one of the axes, that doesn't have one of its coordinates being 0, 2, 2, is that also on the line? It does appear that it is. Now, of course, when I'm drawing these by hand, it's never going to be perfect. There's always a bit of margin for error, but I see that it's like over here and it's not, over there somewhere. It looks like it could reasonably be on the line. So even though 2 points determine a line, I usually plot 3 points and one of them acts as a check that way. Any questions so far? Okay, similar example down here. We just have an equation that looks a little different. Up here we had 3y plus 6x equals 18. And here we have our equation solved for y in terms of x. This first example up here is what we might call something like standard form or the general form. And this is what we often call the slope-intercept form, for a reason that we'll see in a couple of sections. But again, the process is still the same. If I choose a value for x, I can find a value for y. If the associated value for y, if I choose a value for y, I can find the associated value for x. So if I choose x equals 1, what does this equation say that y has to be then? Well, y is 3 times 1 minus 1. That's 3 minus 1 is 2. If I choose, say, y equals 14, well, that says that 14 equals 3x minus 1. And I think we can see just by kind of a guess and check method that x equals 5 is going to work here. 3 times 5 is 15, minus 1 is 14. It's not bad to use a guess and check method, when you see it, that can be very efficient. You don't want to be completely reliant on it though, right? You want to know how to solve the equation if you need to. But if you see that, oh, it looks like x equals 5 will work, that's good enough. And then lastly, y equals 0 says that 0 equals 3x minus 1. Well, if I add 1 to both sides, that tells me 1 equals 3x, or x equals 1/3. OneNote loves to be helpful and try to connect all of my lines, but it's not used to dealing with math, I guess. So my points that I'm going to plot are points like 1, 2, 5, 14, 1/3, 0. Now I look at these points and I say, okay, I mean, in theory, these aren't like bad points to plot in theory. But like 5, 14, maybe that's going to be a little bit annoying to plot, but 1/3, 0 is going to be pretty annoying to plot, right? Like, I don't want to deal with fractions, right? I would like on my Cartesian plane for the points that I'm plotting to be at like integer intersections if I can get it. Now, some equations are messier and than others and more difficult to get nice integer solutions. But for this one, I think actually x equals 0 is going to work a little better. If x is 0, we can see that y is -1. I'd much rather plot that than 1/3 comma 0. 1/3 comma 0 is a perfectly valid solution. There's nothing inherently wrong with it. It's just cumbersome for me to actually try to plot. And 5 comma 14, I mean, that's kind of I have to expand my window pretty big to plot this. Maybe I don't want such a big window. So I have values for x that look like 0, 1, and those give reasonable size outputs for y. When I go up to x equals 5, I get a big output for y. I don't want my window to be that big. Again, this is just a preference issue. I don't know, maybe I choose x equals, maybe I could choose x equals 2. That might give me a y value that's easier to plot. Or maybe I'll choose, say, x equals -1. I have some freedom here, right? I can think through the different choices I could make and what the consequences might be. I don't want to pick x equals 100. That's going to give me an even worse, an even larger value for y. But if I pick x equals -1, y is -3 minus 1, -4, I'd probably rather plot that than something like 5 comma 14, which is way up on the y-axis. So maybe I start down the road of, I'm going to find these 3 points, and one of the points or 2 of the points that I find I'm not super happy with, I tweak things a little bit, try to get better points to make my plotting process a little easier. And what do I have? I want to plot 1 comma 2, 0, -1, and -1, -4. Maybe I'll go 4 tick marks on each axis. And here I'll use my first point ended up just fine, 1 comma 2. That x equals 1, y equals 2. That's not a bad point to plot at all. 0 comma -1, x equals 0, y equals -1. That's here. -1 comma -4, when x is -1, y is -4. And I do see that these points do appear to be collinear. They do seem to all 3 be on the same line. So I can imagine, drawing lines through, say, the top right 2 points, and then using the bottom left point as a check. Is it on the line? It is. If it was, say, over here, then I would think I've done something wrong. I want to go back and check my work. But this third point does appear to be on the line, so seems like things are working out okay. Any questions so far? Okay, let me switch my share around here really quickly. And we'll pick a problem or two off of WebAssign just to demonstrate how that's done, how to use the graphing tool on WebAssign. Give me 1 second to get this set up on my end. Okay, so we have our WebAssign window here alongside our OneNote that we use for some Scratch work. I don't want to go into my section 3.1 to 3.3 homework set here. I just made this available. So And let's come down to, say, this example number 3. So this is what the WebAssign graphing tool looks like. Again, there's also a PDF, quick help posted on the Blackboard site. So if you're, if in the future you're struggling with this, you can come back and look at this part of this video, this recording we posted, or you can look at that PDF, whichever one works best for you. But we see we have the question, graph the linear equation y equals x plus 6 by plotting points. So y equals x plus 6 is my equation of interest. And let me pick 3 points. Maybe I'll start with 0, -1, and +1 for x. This will probably give me pretty reasonable outputs for y. If it happened not to, then I might use the information that I gleaned from that process and try to pick better choices for x or y that make things a little easier for me to plot. When x is 0, I see y is 6, -1, y is 5. When x is 1, y is 7. So those are my 3 points. I'm picking a pretty easy problem here because the main focus now is actually going through the graphing tool over here. Now, one thing that students will do is they'll start by clicking the point here and start plotting different points like 0, 6, clicking on 0, 6, clicking on -1, 5, clicking on 1, 7. And you see what that's doing is it's adding points over here. Now, one thing about WebAssign is it can be fairly picky about exactly what you input. I think most of the time, if you input extra points, as long as they're on the line, it's okay with that. But kind of as a general rule, it's good to not have extra stuff on the graph that's not necessary. So we actually don't want to explicitly plot the points like this. So I'm going to come over here and delete these either by clicking X and deleting each one, or clicking my clear all over here and clearing the whole graph. What I want to do is I actually want to use my line plotting tool, which is the second from the top up here. And here's the kind of unfortunate thing about this. If you look at like any menu anywhere, if I click up here, when I click on the 3 dots, the drop down, these are my options that are strictly below the 3 dots. Or if you're in, Word or something and you click like file, for the menu or something, it gives you a drop down below that. Unfortunately, for this little double-ended line tool here, when you click it, it gives you some different options, and it looks like these are the only 2 options. I've actually written to WebAssign and our reps about this, that this is not the way that user interface works, but it looks like it just gives you 2 options and that this is the title of the drop down, so to speak. But actually, this first thing is the option we want. So we want to click the double arrow and then click the double arrow again, and that selects double arrow. If I click the double arrow and click like the line segment, that selects line segment. Or if I click this and select the ray, the line going off in one direction but not the other direction, selects that. If I click and then click the double arrow, I get that. So you have to like click in the same place twice to pick it. That's really the big challenge here, along with just being careful not to plot extraneous stuff. If you plot extra random points, that's going to mess up the solution as well. And frankly, if you plot extra random points in wrong places, that's not the right solution anymore, to be fair to WebAssign. But there is this little user interface goofy thing where you have to click this and then click in the same spot a second time. And you see that now the 2 arrow, the actual line tool is selected. Now I'm going to pick 2 of these, say 0, 6 and -1, 5. I'm going to click on the point 0, 6. I'm going to click on the point -1, 5. When I have that line tool selected and I click on 2 points, it then draws a line through those 2 points. and it gives me a line over here. This is called line 1 and not point 1 or point 2 because it's a line. Now, supposing I said, oh wait, I clicked 0, 6, I actually wanted 0, 7. I could go through and delete my line and redo it, but I could also come into here and it tells me explicitly what the 2 points are, the X and Y values for my line, 0, 6 and -1, 5. If I wanted 0, 7 instead, I just switch that 6 to a 7. It updates automatically. If I had a fractional value, it's not gonna, when I click something over here, it's gonna try to snap it to an integer point or to at least one of kind of the crosshairs on this graph. So ideally, I would choose points that are easy to click on the graph, but maybe I end up with 0, 6.5. I could click 0, 6, come in here and just edit that to 6.5, and you see it does update the graph to 0, 6.5 for that point. So I can edit the line very carefully and very accurately within this tool here. Occasionally, I might want to use a dashed line. I can make that change as well, making a dashed line instead of a solid line if I wanted to. In this case, I don't want to, but we might see some application for that later on. So at this point, I think that this looks good. I have my third point, 1, 7, and I'm just going to visually check that. Does it look like this line that I've plotted goes through 1, 7? Yeah, it looks perfect. I'll come down here and submit answer. And looks good. So again, just to recap, don't plot extraneous stuff like extra points at random parts of the graph. That's not going to work. If you have an extra point on the line, WebAssign is usually okay with that. But sometimes it gets a little finicky, right? I mean, sometimes it can be a little bit hard to tell if a point is exactly on the line or not without inspecting the specific coordinates of the point. So as a general rule, if it's asking you to plot a line, if you want a little bit of help, if you want to plot some points, draw your line, just erase your points, right? It asks for graphing the line. Just erase your points before you submit it. If you want to use a couple points to kind of help you and make sure that everything is working right, get your line in there. When you're happy with everything, just erase your little points. So you just have the line and then submit it. That's the one thing to watch out for. The other thing is when you're using this tool, again, you have to click. That makes the like drop down, and then you have to click the exact same spot to select the most commonly used thing, the line. So those little two idiosyncrasies, again, not the end of the world kind of things, but they can be frustrating if you're not told to look out for them. You can come back to look at this part of this video or that PDF that's posted on Blackboard. Either one of those will help you if you're running into trouble at any point. Okay, so I think we can jump down to here. We kind of did through that WebAssign example, we did an example of those previous examples that I had written out here. And let's look at just a couple last examples before we call it a day. So here we're given a prompt with not a whole lot else to go on. Graph the linear equation 2y minus 4x equals 15 by plotting points. Okay, so one thing that I notice about this is my right-hand side is an odd number, an odd integer. My left-hand side, 2 times y minus 4 times x. Any integer choice for x and y, say like 0, 1 or 3, 4, that's always going to be an even number. Because I have 2 times one of them and 4 times the other one, and I'm just subtracting them. I can never get even number equals odd number. This is kind of an unfortunate situation where I'm going to have a fraction. It's going to turn out that way. I would rather have a fraction like, 3 halves than a fraction like, 17 sixteenths or something. So I can still have better fractions or more annoying fractions, but I want to just be aware that, I'm going to be stuck with a fraction. So I have to set myself up here. I have to remember that I probably want to pick at least 2 and probably 3 points. Let me start with x equals 0. If x is 0, then 2y equals 15, or y equals 15 halves, or 7.5. If I try to set y equals 0, I have negative 15 fourths for x. I probably don't want to deal with fourths. I'd probably rather deal with halves, I think. So if I pick, say, x equals 1, 2y minus 4 times 1, or minus 4, equals 15. 2y equals 19, y equals 19 halves. Or that's 18 halves plus a half, that's 9.5. And maybe I go down to x equals negative 1. 2y minus 4 times negative 1, 2y minus a negative 4, 2y plus 4 is 15. 2y equals 11. Y equals 11 halves, or that's 5.5. So in this case, I'm stuck with fractional results. There's really no way around that. There are no integer solutions to this equation. But again, I can, find find solutions that are, not so bad, or other solutions that are much more annoying. I would like to stick with, the fractions that aren't so bad. So I have 0, comma 7.5, 1, comma 9.5, and negative 1, comma 5.5. And I just put that right in the way of my dot. And that's my line. Might not be perfectly to scale, but trying to get it in under the wire here. And as a practice, you can practice this as an exercise. You can practice this problem, y plus 5 equals 2/3 x. Go through it, try to find some good solutions, plot them, and we'll knock this one out when we come back and move on to the next sections.